The orthogonal projection of a point in R2 onto a line through the origin has an important analog in Rn. Given a vector y and a subspace W in Rn, there is a vector y hat such that y hat is the unique vector in the subspace W for which y minus y hat is orthogonal to W. Y hat is the unique vector in W closest to y. So this plane here, this rectangle that I've sketched, think of it as the span of a couple vectors in W. And again, I'm just staying with an R2. We have a line that passes through the origin, vector y. Basically what you're looking for is an orthogonal projection is if you go directly to subspace W, there's a 90-degree angle, and the location on W where that happens is we're calling y hat. It's the projection of y on the subspace W. Wherever a vector y is written as a linear combination of vectors, u1 through un in Rn, belonging to the set Rn, the terms in the sum for y can be grouped into two parts so that y can be written as y equals z1 plus z2. z1 is a linear combination of some of the u vectors from this u through n set, and z2 is a linear combination of the rest of them. Let's make a note here. W with it looks like an upside down capital T, but that's actually a symbol for orthogonal. W with this notation denotes the set of all vectors orthogonal to a subspace W. Let u1 through u5 be an orthogonal basis for R5, and we're going to let vector y be a weighted expansion of 5 weights, C1 through C5, multiplied with each of those 5 vectors. Consider the subspace W, which is only the span of the first 2 vectors, and write y as the sum of a vector Z1 in W and a vector Z2 in W orthogonal. So what we'll do is we're going to take those 5 vectors and their weights, split them into the first 2. We're going to call that Z1. And then the rest of them are the back 3, and we'll call that Z2. Z1 is the first 2 weights and vectors, and they are in the span of U1 and U2. Z2 is the back 3 out of the 5 vectors and weights, and that one's in the span of U3, U4, and U5. To show that Z2 is in the orthogonal complement of W, again, that's the new notation, it suffices to show that Z2 is orthogonal to the vectors in the basis of the first 2, U1 and U2, for subspace W. Using properties of the inner product, we're going to compute Z2 dot U1. Z2 was the weight and vector for the last 3. We're going to dot that with U1. Multiplying through, we're going to get C3U3 dot product with U1, and carrying it through, all those dot products are going to go to 0 because U1 is orthogonal to the last 3. A similar calculation will show that Z2 dotted with U2 will be 0 as well. And so Z2 is in the orthogonal complement set. The orthogonal decomposition theorem, let W be a subspace of Rn, then each y in Rn, y being a vector, can be written uniquely in the form y equals y hat plus z. Y hat is in subspace W, z is in the orthogonal complement of W. In fact, if we take p vectors and they are an orthogonal basis of W, then y hat can be computed with the following dot product and multiplication. Y dotted with U1 over U1 dotted with itself, all the way through the p vector. Z is going to be denoted as y minus y hat. So we'll have to calculate y hat first, and then we'll take y that's given and subtract that calculated vector from it. So let's jump into an example. Let U1 be this vector, 2, 5, negative 1. We're going to let U2 be this vector, negative 2, 1, 1. And y is going to be the vector 1, 2, 3. Note that U1 and U2 is an orthogonal basis for W, which is the span of those vectors. 2 times negative 2 plus 5 times 1 plus negative 1 times 1, negative 4 plus 5 is 1 plus negative 1 is 0. If your dot product is 0, then your vectors are orthogonal. Write y as the sum of a vector in W and a vector orthogonal to W. This is where we have to calculate y hat. Okay, so let's take this part first. Y dotted with U1, 2 times 1 plus 5 times 2 plus negative 1 times 3. So we have 2 plus 10, that's 12, minus 3 is 9. That's where this 9 comes from. U dotted with itself, U1 dotted with itself, 2 times 2 plus 5 times 5 plus negative 1 times negative 1. Basically, you square each number, add them together. 4 plus 25 is 29, plus 1 is 30. And that's where this denominator comes from. Times U1 itself, so that this and that will be multiplied with your final answer from those two dot products, plus y dotted with U2, negative 2 times 1 plus 1 times 2 plus 1 times 3. Negative 2 plus 2, that's 0, plus 3 is 3. And then U2 dotted with itself, negative 2 squared is 4, 1 squared is 1, another 1 squared is 1, so 4 plus 5, and then a total of 6. I kind of said that wrong. 4 plus 1 is 6. That's where this 6 comes from. U2, we're going to set it next to it and multiply. If you carry out the multiplication and then the addition, you will get this vector. Y hat takes quite a bit to solve. Please use your calculators carefully. Once you've got y hat, then we can calculate z, because z is going to be the original y minus y hat. Well, the original y is 1, 2, 3. Y hat we just calculated, and then we subtract them. 1 minus negative 2 fifths, that's the same as 1 plus 2 fifths, 7 fifths. 2 minus 2 is 0. 3 minus 1 fifth, well, that's 2 and 4 fifths, but as an improper fraction, it's 14 fifths. Therefore, you can decompose vector y, which was 1, 2, 3, as y hat. Now remember, let's go back to the top. We're going to decompose it as y hat plus z. Y hat was the hard part to calculate, so we have y hat plus z, which we just calculated here. And so y hat plus z is the way to decompose this vector. The best approximation theorem, let W be a subspace of Rn, let y be any vector in Rn, and let y hat be the orthogonal projection of y onto W. Remember from the first slide, y hat is if you follow a line through the origin, and then from the where y ends on that diagram, if you go straight to subspace W where you create a 90-degree angle, that's orthogonal. Then y hat is the closest point in the subspace to y, in the sense that the magnitude of y minus y hat will be less than the magnitude of y minus v, as long as vector v is distinct from y hat. Let's do an example. Let u1 be 2, 5, negative 1. These are very familiar. We just used these on the previous example. u2, same. Y, same vector. W is the span of u1 and u2. Now remember, their dot product is 0, so u1 and u2 make an orthogonal basis. Let's calculate y hat. Same dot products as the previous example. Now down here in the recall section, I kind of wrote out what I verbally described on the previous slide. So feel free, if you got confused on the previous slide, just use these as a reference for those numbers. We calculated y hat to be a vector with these 3 entries. And that's your orthogonal projection. Let me move up to the next slide. And let's actually calculate the distance from a point y in Rn to a subspace W. That is defined as the distance from y to the nearest point in W. Find the distance from y to subspace W where, and now these I've changed it up a little bit. Y is the vector negative 1, negative 5, 10. U1 is the vector 5, negative 2, 1. U2 is the vector 1, 2, negative 1. Now, down here we're making the claim that U1 and U2 form an orthogonal basis for W. Let's just quickly check the dot product there. 5 times 1 plus negative 2 times 2 plus 1 times negative 1. So that's 5 minus 4 minus 1, and that gives us 0. So U1 and U2 do form, the set of those two vectors is an orthogonal basis for W. All right, now we're going back to the problem where we're asked to find the distance from a point y, and that's a point in space, to the subspace W, which is the span of those two orthogonal vectors. All right, let's get to it. That's the y hat. So we have y1 dotted with u1, negative 1 plus 5, plus negative 5 times negative 2, plus 10 times 1. So where this 15 comes from is negative 5 plus 10 plus 10. The denominator is u1 dotted with itself. 5 times 5 plus negative 2 times negative 2 plus 1 times 1. 25 plus 4 is 29 plus 1 is 30. This other fraction, I'm going to hold off u1. We're just going to grab that vector and drag it down. This number, negative 21/6, that is y dotted with u2 So we have negative 1 times 1 plus negative 5 times 2 plus 10 times negative 1. So that's negative 1 minus 10 minus another 10. That's negative 21. The denominator 6 is u2 dotted with itself. 1 times 1 plus 2 times 2 plus negative 1 times negative 1. So that's 1 plus 4 plus 1, and that's where the 6 comes from. Multiplying 15 over 30 by vector u1, you can reduce these two if you want. So 15 over 30 is a half. Just be very careful when you calculate. This fraction reduces to negative 7 halves, and that's why that changed to negative 7 halves, times u2, so that's where I drug that down. And then if you carefully multiply and then subtract, this will be your projection of y onto subspace W. Now that's a mouthful. Y hat is the projection of vector y. So if you were to plot this in space and then make a direct path to subspace W where it formed a 90-degree angle, that's what y hat is. That's the point on the subspace that is 90 degrees from vector y. Now subtract original vector y minus y hat that we just calculated. Negative 1 minus negative 1 is 0. Negative 5 minus negative 8 is 3. And 10 minus 4 is 6. For magnitude or distance, we're going to square and add each entry. 0 squared plus 3 squared plus 6 squared. Well, that equals 45. And so the distance from vector y to subspace W is the square root, and this is Pythagorean theorem, square root of 45. And since 45 is 9 times 5, square root of 9 is 3, the 5 stays under. Theorem: if you have a set of vectors 1 through p and they are orthonormal. Now remember, orthonormal is orthogonal and unit. So they are vectors that are orthogonal and also have a unit length or a length of 1. So if those p vectors is an orthonormal basis for a subspace W of Rn, then your projection of vector y on subspace W is simplified a little bit because you don't have to mess with that denominator. You don't have to do a u1 dotted with itself, a u2 dotted with itself like we did on the previous example. It's just a single shot. Because the distance or the length is 1, all these have a denominator of 1. And that helps out a bunch. We're going to let capital U be the matrix of those p vectors in this set. And then once we've defined matrix U using each of the unit orthogonal vectors, the projection of y on subspace W can be calculated by matrix U times its transpose times the original vector y, and that's for any vector y in Rn. Let's jump right into an example. Excuse me. We're going to let vector y be 5, 10, 1. u1, now remember, orthonormal. If you were to square each number and add them together, you would have 1/9 plus 4/9 plus another 4/9, which is 9/9. That's a total of 1. So remember, the length is 1. Square root of 1 is 1. Same thing for vector 2. Squaring and adding 4/9 plus 1/9 plus another 4/9 is 9/9. That's 1. Square root, you got 1. So that is just how to make sure they're orthonormal. their dot product adds up to 0, so that's the ortho part. The normal is unit length 1. All right, so we're going to claim that W is the span of U1 and U2. All right, let's build matrix U. This part up here, if capital U is the matrix formed by U1 and U2, if we had more vectors, we'd have more columns. So that's U1, U2 stacked vertically. The transpose, column 1 is row 1. Column 2 is row 2. U transpose times U transpose times U. Be super careful. I recommend using a calculator or a matrix calculator online, but U transpose times U actually comes out to an identity matrix I2. A couple of ones on the main diagonal. Now, we know that matrix multiplication doesn't always lead to the same answer if you switch the order. So we don't expect this to come out to the same answer. In fact, it's way off. If you were to multiply it in reverse order, where you take matrix U times the transpose, you get a 3 by 3 matrix due to dimensions. U times U transpose gives you this 3 by 3 matrix. Well, if you sprinkle in a multiplication by vector Y, U times U transpose, that's this 3 by 3, times vector Y, you will find a vector that is the orthogonal projection of the original Y on subspace W. Again, think of it as a sheet of paper with an arrow through it. Pick a spot on the arrow, go to that sheet of paper directly, making a 90-degree angle, and where you land on the paper is an orthogonal projection. I hope this helps. This is actually the last video of the class. You guys have been fantastic. Stay strong through the last few weeks. If you have any questions come up, please ask. I can be reached by email. That's actually the best way to contact me, jerry.west@uafs.edu. And I look forward to hearing from you if you have any issues. If not, I assume no news is good news.